Hello all, my name is Richard Nugent. I'm an economist and the lead developer for the HEC FDA program at HEC. This series of videos serves as an introduction to some of the hydraulic relationships that we define in the FDA program. In this video, we'll take a look at inflow-outflow transform functions. A transform flow relationship may be used to define a relationship between unregulated and regulated flow, inflow and outflow, or another relationship to transform the flow defined by the discharge probability function. This transform flow relationship could be the result of a reservoir or channel routing, channel diversion, so on and so forth. Although a graphical curve could be used to represent a regulated probability function, it is better to first derive an unregulated curve and then use the transform flow function to convert the unregulated curve into a regulated curve. Starting with an unregulated frequency function and bringing in an inflow-outflow transform function allows for the isolation of the uncertainty related to the transformation mechanism while still maintaining the uncertainty of the discharge probability function. Using this method also allows us to use the log Pearson type 3 distribution to define the unregulated flow probability function. In the charts at the bottom of the slide, an unregulated flow exceedance probability function is plotted on the left and is scaled against a regulated discharge function in the middle. Observe that the reduction in peak flows translates to a flattening of the flow exceedance probability function as seen on the right. In the case of an unregulated flow for a given event or probability of exceedance, we can identify a peak discharge from the flow exceedance probability function. The identified peak discharge corresponds to a particular stage from the stage flow or rating function. The identified stage corresponds to a level of damage on the stage damage function, and relating this level of damage to the probability of exceedance from the flow exceedance probability function gives us a probability that the level of damage is exceeded from the damage exceedance probability function. In the case of a regulated flow, as with the case of a dam, the dam will hold back flows for large events, low frequency events, so that peak flows are reduced. And this will continue until the dam becomes dangerously full, at which point releases would increase. Now for a given flow, the stage stays the same as nothing has been changed about the channel that would alter the rating function. For a given stage, damages are the same, assuming that the dam has not done anything to encourage or discourage development. However, because the dam has decreased the frequency of certain peak stages, the dam exceedance probability function is truncated. So what we see is that the inflow function may be represented by the black flow exceedance probability function in the top right, and the outflow function is equal to the inflow function except where the red dashed line breaks away from the black line, in which case the outflow function is represented by the red dashed line. And the effect of this is the reduction in damage, and we can see the reduction in damage as given by the difference in damage for a given probability of exceedance. You can see that on the plot by the difference or the difference between the two points, the red point and the blue point. Let's take a look at the mechanics of defining an inflow-outflow transform function. First, the unregulated analytical discharge exceedance probability function is defined. Second, enter the log Pearson type 3 distribution statistics. The transform function will not be available if synthetic statistics are computed. Third, enter the mean, standard deviation, skew, and equivalent record length to define the log Pearson type 3 distribution. Fourth, the uncertainty about the discharge exceedance probability function will be calculated after the log Pearson type 3 distribution characteristics are saved. Fifth, select transform flow regulated versus unregulated. Sixth, select the type of uncertainty distribution to use around the transform function. And seventh, define the function with uncertainty. In this case, a triangular distribution has been selected, and a minimum, most likely, and maximum outflow has been entered for each inflow. Observe in the transform flow plot for several levels of inflow, outflow is constant with near certainty. Definition of an inflow-outflow function is necessary to isolate the uncertainty related to the transformation mechanism while maintaining the uncertainty of the inflow discharge probability function. The uncertainty around the inflow discharge probability function can in large part be attributed to natural variability and is based on the period of record. However, the uncertainty around the way that inflows are transformed into outflows comes from knowledge uncertainty, such as operational decisions and the ability of a reservoir to manage different volumes with the same peak inflow. Because each process has a distinct type of uncertainty, we want to include the processes in the simulation individually. Let's take a closer look. The uncertainty around the inflow-discharge frequency curve follows a known probability distribution, the log Pearson type 3. Hence, we can define with a certain level of confidence a range in which we expect to find a peak flow for a given frequency. If the estimate of the flow is off, then we find ourselves in a different location on the inflow-outflow function. However, if the estimate of regulation is off, then the shape of the inflow-outflow function may be different altogether. This highlights the importance of including these processes individually. An alternative to the method described in this video is using a regulated graphical flow frequency function as opposed to an unregulated analytical flow frequency function with a transform flow function. Graphical flow frequency functions typically only come into play when the distribution of flows cannot be described by the log Pearson type 3 distribution. Doing so, however, limits the ability to properly define uncertainties in the flow and will result in unusual uncertainty values. If you have any questions, please feel free to reach out to me, Richard Nugent, or post your questions to the Discourse discussion board.